Huh. Why is it doing that? Why is it still showing that? Oh, yeah, because I only have 2 lamps rigged up at this point. That's right. That's right. Maybe that's what happened earlier too. Okay, so here we go. 1.5, 4.5, which splits up into 3, 4.5. So if I put this one here instead, I'm not sure if this is going to work here. There we go. 4.5 total, 1.5 in this one, 1.5 in this one, and then I think you can believe that's 1.5 in this one. And I showed that each one of these here has 6 volts across them, so each one of them gets 9 watts, which is the same as it was in the simple single bulb circuit earlier on, and a total of 27 watts. Okay, let's go back to the other part of the problem. So here it says for a parallel circuit of 3 different resistors with resistances 330 ohms, 560 ohms, and 680 ohms, and a voltage source that provides 60 volts, compute the total resistance and the total power output. So the circuit is going to look as such. I think I need a little bit more space here. There's 1, 2, 3. Sorry that I counted, didn't have to do that, but here we go. So there's the ammeter. Maybe I'm talking to myself here so I won't forget anything. There we go. There. And there. And I guess drawing them vertically, I'm not that good at it. There we go. Alright, so this one is 330 ohms. I remember the last one, 680 ohms. And the one in the middle was 560 ohms. And this one over here is 60 volts. Okay, the same rules would apply. Each device connects to the same 2 points of the circuit. The voltage is therefore the same across each device. So actually that one we do know, 60 volts across each one of these. Okay, then the current divides among the parallel branches. Ohm's law applies separately to each branch. So each one of them is going to get some current. By the way, which one gets the most current? And you may have heard this before, the path of least resistance. And that indeed is this one here, the one with the 331 will end up with the largest current. And I'll show you in just a moment because it says Ohm's law applies separately to each branch. So I1, the individual current for the first resistor, would be 60 volts divided by 330 ohms. And I do that separately here. I come up with 0.18 amps. Then the one in the middle, I2, equals voltage divided by the second resistance, 60 volts divided by 560 ohms. That looks like a little bit more than 0.1 amps. And I come up with 0.11 amps, rounded. And the third one is over R3, 60 volts divided by 680 ohms. So it looks a little bit less than 1 amp. And I come up with 0.09 amps rounded. So those are the 3 currents going through each of these resistors here, and they add up to the total current that flows through the circuit, where it says the total current in the circuit equals the sum of the currents in its parallel branches. So it's going to be that the total current, as written above for the other circuit, for the light bulb circuit, is I1 plus I2 plus I3 equals 0.18 amps, 0.11 amps, 0.09 amps, equals 0.38 amps, and that is rounded, so 0.38 plus or minus a little bit. So that's the total current. Well, that in turn will give me the total power for the entire circuit as total current times voltage, 0.38 amps times 60 volts, and again I do that on the side. That looks a little bit more than 20 watts, and I come up with 23 watts. That answers one of the questions. The total power dissipated is 23 watts. As far as the total resistance is concerned, so the equivalent or total resistance, that's the voltage divided by the total current. So that is going to be 60 volts divided by 0.38 amps. Look, somewhere around 150 or so. Let's see, I come up with 160 ohms. It's 157.89 ohms, but I rounded to 160 ohms because I only have two significant figures here. Okay, so this is the total or equivalent resistance, 160 ohms, which is in accordance to what it says about the resistance. As the number of parallel branches is increased, the overall resistance of the circuit is decreased. So as I add the 560 and the 680 to the 330, the overall resistance needs to be decreased from the initial one. And then overall resistance lowered with each added path. This means the overall resistance of the circuit is less than the resistance of any of the branches, or in other words, the equivalent resistance is less than the smallest resistance. So it has to be less than 330, and indeed I came up with 160. However, how do you put 330, 560, and 680 together in order to come up with 160? And for that, I'm just going to present that, how resistances are added in parallel, and that is as reciprocals. The equivalent resistance equals 1 over R1 plus 1 over R2 plus 1 over R3, and if we had more of them in parallel, then we would do that. Okay, now let's actually add them up. 1 over the equivalent resistance equals 1 over 330 ohms plus 1 over 560 ohms plus 1 over 680 ohms, and see what the calculator gives us. So let's see, move this over a little bit, and the calculator, it's good. Alright, let's see. 1 divided by 330 plus 1 divided by 560 plus 1 divided by 680. Hit enter, and I come up with this number here, 0.0063 rounded. 0.0063 0.0063 rounded, but that's not the end result because I still have to invert that because it says 1 over the equivalent resistance equals this number here. And the units, by the way, at this point here are 1 over ohms. I need to have ohms as equivalent resistance. This is a typical mistake stopping right here. This is not the equivalent resistance. If you get a number that is as small as this one here, almost ridiculously small, that is not the correct number. Instead, that needs to be inverted one more time, so 1 divided by that answer comes indeed out to the 159.0 that I had earlier on my calculator, or I calculated 157.9, but that's within rounding in between. Still, that rounds to 160 ohms as well, which is the same as calculated earlier using the rules for a parallel circuit and eventually coming up with the equivalent resistance. Let me just show you on a graphing calculator the way I usually do it. I open the parentheses, I type in my first resistance, and I know where the button is for to the -1, which is invert my number. Plus 560 plus 680, and then I close the parentheses, and now if I do that I come up with that really small number, the 0.0063, but I know I need to invert it, so after I close the parentheses I do again to -1, which inverts it again, and that's why I put parentheses around this right away. So in parentheses I invert each one of the numbers as I add them, and then after I close the parentheses I invert it again, which then will give me this equivalent resistance, and when I hit the enter button, indeed I come up with the 159. Okay, let's look at the simulation. On this one here, I'm gonna remove the light bulbs. It always wants to hook up to this one here. There we go. Jeez. Oh yeah, I have to remove that light bulb there first. Alright. And actually I will put yet another ammeter right there, and then I will put the resistances there. There we go. There we go. If we get readings right now, don't pay attention to them because I actually still need to change resistances and the voltage here. Whoa! Okay. That doesn't look good. My battery in flames. Oh no! Oh, that's a bummer. I didn't realize that. Did you just see that? In this applet, I can only go between 0 and 100 ohms. So I have to fake this here a little bit. You'll see in a moment. Let's see. Show value. Okay. Let's see. Oh, there we go. Show value. Show value. Show value. So what I did instead is I kicked each of the resistances down by a factor 10, and I kicked the voltage down by a factor 10. Notice that nevertheless the amps that I get, the total current is the same, 0.38 amps, and the way that it splits up is the same as we had calculated earlier as 0.18, 0.11, and 0.09 amps, and that is because I divide by a number that I divided by 10 and divide that by another number that was divided by 10. So actually for the currents that doesn't matter. And then for the total power I come up with 0.38 amps actually by our original 60 volts, which was I believe 27 or 23 watts. And then, oh yeah, as far as the voltmeter is concerned, yeah, we still get 6 volts across here respectively from the problem, actually 60 volts. And yeah, unfortunately it doesn't allow me more than 100 ohms here. That's why I had to kick these numbers down.